Hello, my name is Kazimierz Murzyn. I'm Managing Director of LifeScience Cluster Kraków. Welcome you on the Bioeconomy session on LifeScience Open Space event 2020-2021. That's difficult, yeah. Today with me in the LifeScience Open Space studio, there are guests, distinguished guests and leaders of this subject, bioeconomy. Let me introduce Maciej Guzik, Dr. Maciej Guzik, who is sitting next to me and who will be leading this session together with the invited guests and guests invited through online, yeah, or through web services. What will be the session all about today?
Good morning, everyone. So today we'll be talking about bioeconomy within Europe, and we have divided this section into two consecutive parts. So first part will be on general bioeconomy, how it is done in Europe, and on example of two different countries, so Serbia, Poland, and then we'll move to example sessions where we will see how actually it is working. So today we will start with a lecture of our keynote, Professor Aleksander Steinbichel. He is affiliated with Politechnika Łódzka, Łódź Polytechnic, and he will deliver a lecture on perspectives for extended recycling of biopolymers in a circular economy. So Alexander, the floor is yours. And we can, I think, start the presentations when it will appear on the screen.
Okay, thank you very much for the introduction and also for the invitation. The time is relatively short for my lecture, so I will give a general overview at the beginning and then one concrete example. Polymers are very important compounds, and a vast number of different polymers is produced by the chemical industry, by biotechnology, and most of these polymers are, of course, needed, and many more polymers will be needed in the future, and there's an intensive research in the chemical industry for new polymers, for new combinations of polymers, new polymeric material. But these polymers, as we all know, create a lot of problems in the environment. Most of them accumulate in the environment after use, and the pollution of the environment is due to lacking or not functioning waste management strategies and by littering. There's a need for depositories and dumps. There's the utilization of fossil resources from which they are mostly produced currently. And this also can be changed, and there's no sufficient integration of the polymer production and polymer use in the circular economy. And this results often in these terrible pictures, as I have shown you here. And you know all these similar pictures from huge amounts of plastics which accumulate in the oceans. So in the oceans are probably about one annual production of polymers floating around, accumulating in certain areas. But there are also some minor problems which are not that obvious. For example, xerocopied paper. On the left side, you see a culture of cellulomonic bacterium, Cellulomonas fimi, which uses the cellulose from the paper sheath and degrades it completely. So the solution becomes turbid due to the increase of the number of bacteria. But you see that some parts are not degraded, and these are the letters, because these are letters consisting of carbon and non-biodegradable plastic, and considering the amount of xerocopied paper sheets which are produced each day all over the world, this is really a big problem, and this excludes these compounds from measures processes of the circular economy. So how can polymers be used after their use? They can, of course, be dumped in landfills and similar dumping locations, but this is not a real solution, or not a solution at all. They can be terminally used. Some of the materials can be recycled as materials, and certainly one of the best and most flexible solutions would be the recycling of the molecules or the conversion into other polymers, into other materials. And for this, I will give an example. And this are parts of future circular economies. I use the word plural because the circular economy will not be the same for all compounds. There will be several different strategies occurring. And these circular economies provide a process to recycle the used materials, the polymeric materials, several times, whereas the linear economy will use up valuable resources, and they will result in the production and accumulation of unwanted materials. That could be materials which are ending up in the dump landfills, but this can be also carbon dioxide, methane, and so on. And this is something which we have to avoid. On this slide, I will come now to a concrete example. The annual consumption, global consumption of polyisoprene rubbers is shown, and synthetic rubbers and natural rubbers amount up to about 30 million tons per year. That's a large amount. That's about almost 10% of the total polymers produced by the chemical industry, and you see that there's a huge demand for rubbers, and these rubbers must come from natural sources, Hevea brasiliensis, and they can also come from synthetic sources by the chemical industry. You very nicely see here where the economic crisis about 10 years ago was located, by the drop down of the annual consumptions. So these are large amounts, and rubber compounds, mostly tires and some other compounds, are very complex material. They consist of natural rubber, they consist of several synthetic type of rubbers, and only two examples are mentioned here, and they consist of vulcanized rubber. And this is very important because tires would not be possible to produce without vulcanized rubber. This changes the structures, and this also makes the recycling and the inclusion of tires in the circular economy very difficult. Here you see the complex composition of tires. That's not only different types of rubbers, which I have mentioned before. These are also textiles, these are metals and many other compounds, and these are a lot of additives which are summarized on the next slide. One of the most important additive, at least from the amount, is a black carbon filler. Then you have antioxidants, you have accelerators, and many, many more compounds. That makes the rubber to a material which can be used by for the manufacture of tires. And if all these compounds would not have been added, then tires could not be produced, and many other products manufactured from rubber. And if all these compounds are not present, the material would be much more easier degradable and biodegradable by enzymes, by microorganisms. And most of these compounds and also the structure of the rubbers prevent an efficient biodegradation of used tire materials. Normally, polyisoprene as a natural product, as a natural polymer, is quite reasonable, biodegradable by different microorganisms. One possibility could be to modify the rubber materials after the polymerization by enzymatic and by chemical measures. And different processes have been developed, or are possible at least. I will start first with the chemical modifications. For example, the click chemistry strategy can be very efficiently applied for such molecules because they have double bonds. They may also contain some functional groups which are accessible to the compounds of the click chemistry. So click chemistry is an important tool for the post-polymerization modification of rubber and other polymers. It does not move forward. Here you see some examples of the click chemistry approaches that can be applied to rubbers. I will not go into detail on this, but you see that double bonds, triple bonds, and some groups, chemical groups, are required, and they are available to modify the rubber molecules after use. I don't know whether it's... And so this is one approach. The other approach is to use enzymatic methods, which are environmentally friendly, and there are a lot of enzymes have been isolated and characterized in much detail who can degrade rubber molecules, and they are produced by microorganisms which use rubber as a carbon source. And these enzymes are, of course, extracellular enzymes which are secreted by the microorganism. And here you see some of these enzymes from the toolbox. These are rubber oxygenases which add oxygen to the double bond present in natural rubber and most of the synthetic rubbers. There's a ROX R, LCP, latex clearing protein, ROX B, and many others which attack rubber molecules either from the terminal regions or can also cleave within the molecules. And with this you can produce low molecular weight compounds, oligomers, or just polymers with a reduced. This next slide just shows one very simple example how rubber can be used in a circular process. On the left side you see tires which have to be grinded, which in order to enlarge the surface, and they might be also pre-treated by different mines, and in a bioreactor you can then add either bacteria or enzymes, and then you will obtain functionalized particles with a different surface, and you will have so-called liquid rubber, which mostly consists of oligomers, and this can be recombined to produce some new rubber materials, some new tires, for example. And this is actually followed up by the industry. We had a long-lasting collaboration with the German company who is following up this strategy, and coming to an end, and the summary and conclusions. There are a lot of examples using Diane rubbers as used materials, and to convert them into materials for new uses. And it has been shown that these strategies can not only be applied for rubber materials, and is open for many other polymeric compounds as last as they are accessible to chemical substances or to enzymes, and such processes will provide novel materials and will contribute to the circular economy, thereby saving also carbon, which will be very important. And we should now go to the last slide. I would like to acknowledge the work of 3 postdocs or PhD students, Franciela Soares, Anna-Lena Altenhoff and Rodrigo Andler, who did either in microbiome at the Technical University in Lodz first studies, or did extended studies at the University of Münster, where I'm coming from. These activities are supported by the Foundation for Polish Science by the European Union, and the company which we had contact with was Freudenberg Technologies. And I would like to encourage scientists from the biological side and also from the chemical side to follow up these strategies and to explore these synthetic modifications to develop new elements for the circular economy, and also to develop new processes, new materials. Thank you very much for your attention.
Thank you very much, Alexander, for this great talk. We'll bring it later into the discussion. But now let's move to another speaker, who is Damian Kuznowicz from Foundation of Education and Societal Dialogue ProCivis. And he will be talking about a very important aspect, that is actually creation of bio-based education centers in Europe. As we know, without education there is no progress. So please, floor is yours.
Okay, thank you. Let me share my screen. Okay, let's start. Hello, everyone. My name is Damian Kuznowicz. I'm a project coordinator in ProCivis Foundation. Today, I would like to present our latest project and our offer of cooperation on this project, and perhaps on in other areas. Maybe I'll start with a short introduction of our foundation. ProCivis is an NGO. We're working to integrate business and science. We support cross-sectoral partnerships between institutions. We are also member of Bio-Based Industries Consortium and member of BioBoard Baltic Sea region, which is Bioeconomy partnership with Scandinavian countries and other countries in Europe. We also support some works on educational systems to develop some innovative and friendly ways to develop education. And the last thing, we also have some experience in technology because we are leader of business science partnership, and we are managing a pilot installation of biomass cascade extraction. The full name of our project is preparing the creation of bio-based education centers to meet industry needs and boost the contribution of the bioeconomy to societal challenges. So the project has received funding from Horizon 2020. So the key aims of our project is to build bridges between the bio-based industry and educational systems. So we want to link in our project universities, innovation labs, or R&D centers with industrial actors and regions administration. So in our project, we want to develop a holistic framework that connects the traditional idea of education with a knowledge hub. So we want to develop framework that will create a multi-level bio-based economy education centers that will fill the gap between academic institutions, students, innovation centers, and business industry. So we want the BBECs, as we call them, so the bio-based education centers, to be flexible enough to answer actual and future needs of industry in cooperating with science. So in this project, we want to involve multiple stakeholders. We can see on this slide, we want to involve academia, informal education, industry, NGOs, government units, and multiplicators, as we call them. So the institutions in every European country that could replicate the models. So in our project, we want to create six frameworks of BBECs, of education centers, that it will be model framework that could be replicated in other countries. So very briefly about the objectives. So we want to align the needs for skills in bio-based economy industry. We want to prevent skill gaps in the bio-based industry. We want to maintain industrial activities and boost jobs. We want to increase amount of jobs in bio-based industry, and in general support education and learning opportunities for our stakeholders. So our consortium is quite big. It's there are 19 partners. Our project leader is University of Bologna. Our other partners are some important academic units like University of Hohenheim or Dutch Wageningen. There are also consulting companies, NGOs from around Europe. in Poland, there is Procivis Foundation and Educational Research Institute from Warsaw. So on this slide, I just wanted to show the implementation of our project. Maybe it's a bit complicated, but I think that the most important thing is in the middle, because we can see there the 6 we will represent the model for Central Eastern Europe. Other models will be made in Scandinavia or Western Europe and in Ireland. So, like I said, the model framework of these biobags could be replicated in other EU countries. So that's the idea of our project. So cooperation. At this stage of our project, our aim is to identify as many stakeholders as we can that we want to invite in creating our Polish biobag model. So who we are looking for? Okay, stakeholders that provide formal and informal education, training or consulting in the field of bioeconomy, or on the other way, institutions that have educational needs in the field of bioeconomy, so especially business. And the forms of cooperation, I've indicated here 3 forms. How I don't know, institutions or universities can take part in our project. So there could be individual interviews, participation in consulting survey, and participation in national and regional pan-European workshops. Everything will be connected with creating a Polish BBAG or Central Europe BBAG. And we want to identify existing problems, opportunities, and best practices to create our holistic model of cooperation for future. We've made some workshops already and some webinariums, and we can see now on Polish ground there is a huge problem with bioeconomy, because we've diagnosed that, for example, Polish business or sometimes educational institutions don't even know that they are part of bioeconomy. So I think there's a huge job to be done in Poland. So we are happy to invite everyone who wants to cooperate with us. On the last slide, this is my contact. This is our project's website. So if anyone would like some more information, I will be happy to answer. Yeah. So I think that's it. Thank you very much for your attention.
Thank you very much for your presentation, Damian. It was very valuable. Now we will move to another speaker, because the questions will hold in the end of the session. Let's welcome Jasmina Nikodinowicz-Runic from Institute of Molecular Genetics and Genetic Engineering of University of Belgrade in Serbia. Jasmina will shine a light on bioeconomy expertise and collaboration opportunities in Serbia. So Jasmina, floor is yours.
Good morning, everyone. I'm Jasmina Nikodinowicz-Runic, and I am coming from the Institute of Molecular Genetics and Genetic Engineering from the University of Belgrade. I would also like to thank Dr. Guzik for this opportunity for me to give you some details on biotechnology towards bioeconomy in Serbia. Yes, before you reach for your hand sanitizers, it is my talk is about good microorganisms. So I would like to share this concept of upcycling using microbial biotechnology with you. And some microorganisms are literally everywhere. And they are original inhabitants of our planet, and they kept our carbon and other element cycles in balance. But recently, humans are altering this balance, but generating huge amounts of waste. And we are literally breeding, eating plastic waste. As Professor Steinbuchel mentioned, it's a big problem, but we're also generating enormous amounts of food waste. And when talking about pharmaceutical industry, for a kilo of pharmaceutically relevant compound, there is about 300 kilos of hazardous chemical waste generated. So once again, we are going to turn to good microorganisms to try to help us solve this waste situation. And so we are proposing to use the microorganisms that are able to degrade some of these waste streams, but not only for growth, but also to produce some valuable molecules. And then we are proposing to synergize with chemists and biochemists and to optimize these valuable structures because on the other side, while there is a lot of waste generated, we are also finding ourselves lacking new and innovative biomedicines. So in this whole value chain, in the end, we are hoping to produce a sustainable biopharmaceutical and other products that can become part of the sustainable solutions. So let me tell you a little bit about Serbia perspective in all this. On the left, you can see that if we think about bioeconomy and biorefineries as embodiment of the bioeconomy, there is about 803 biorefineries across Europe. And I see the circled area here is Serbia and Western Balkan. There's none of biorefineries in this region. So this region is lagging behind more developed regions in Europe. But on the other side, this time, Serbia is showing some good potential in the sense of innovations. And you can see that that's the European Innovation Scoreboard there on the right-hand side. And there is genuine interest in collaborative efforts in organizing the networks or educational efforts or in introducing some responsible waste management practices that would lead to better bioeconomy in Serbia. And I am actually leading this group for ecobiotechnology and drug development in Belgrade. And there is about 4 or 5 research groups, including our one, that are doing some research within this field. So I am just going to show you a few examples of what we are currently doing. And also, this is also an invitation for collaborative efforts within this area. So we are currently developing a novel biocatalyst based on microbial enzymes. As for the past 30 years or so, my institute has been involved in sampling various soil samples and other samples, and isolating microorganisms and organizing them into culture collection. So we are also looking into using actually producing biopigments from various waste streams. And within our interest is bacterial biopolymers, such as polyhydroxyalkanoates and bacterial nanocellulose. We are searching for new applications for bacterial nanocellulose. And important part of our research is actually the assessment of antimicrobial and cytotoxic properties of different materials and different bacterial products. So the methodology that we are using, as I said, we have a good culture collection, and we turn to it every time we need to solve a problem. And this is where I saw the potential with Professor Steinbuchel's talk and rubber derivatization and maybe metabolizing some of those monomers or oligomers. But at the bottom here, you see an example of, let's say, production of this colored secondary metabolite. Streptomyces are a big part of our culture collection. So we have identified this to be undecylprodigiosin, this molecule. And so in the fermentation, we are able to produce it on the larger scales. And so natural products, they're really a good source for antibacterials or anti-cancer drugs. But usually they don't come to the market before they're optimized in certain way. And by producing large amounts of this compound, we were able to use green chemistry and biocatalysis to produce halogenated version of this molecule that is now tested in against cancer cell lines. And so with these pigments, we also propose to use them as a greener alternative to petrochemical pigments. And you can see here painting made using Streptomyces pigments. Also, with the polyhydroxyalkanoates, we are trying to develop them as ingestible biosensors, and we are collaborating with the group from electrical engineering for this. As I did mention this before, so I'm just going to quickly say that there are abundance of natural products that we can optimize biocatalytically. And we have a good model system, such as zebrafish embryos, that we are testing their toxicity, so avoiding that common mistake of finding a compound and then realizing it's toxic in the end. This brings me to the end of our talk. We already have a good collaborative network within Europe, but we're open for new collaborations. We also are part of the project that is called BioICEP, and it is working on biotechnological solutions for the mixed plastic waste. Thank you for your attention.
Thank you very much, Jasmina, for this nice talk and bringing the perspective of both our countries, Serbia and Poland, being in the emerging innovator sector. So we have a long road to approach. Thank you for that. Let's move now back to Kraków and listen to Mr. Szymon Jarosz from Economic University of Kraków, and he will be talking about towards a sustainable transformation of enterprises. So, Szymon, floor is yours.
Thank you so much. As it said, hello everyone, my name is Szymon Jarosz, and I'm honored to represent Kraków University of Economics, and on behalf of myself and my colleagues, Mariusz Sołtysik and Magdalena Wojnarowska, I'd like to deliver a presentation on sustainable transformation of enterprises. And the aim of this presentation is to present the effects of scientific research in the field of in the field of sustainable development and the impact of innovation on the strategic direction of enterprises' activities. The last three industrial revolutions have been largely driven by the advancement of technology and the increased importance of procedures. But the fourth revolution, on the other hand, represents a shift focused on the right alignment of capabilities and sustainable outcomes. And under these circumstances, there is a growing need for enterprises to develop dynamic capabilities and appropriately adapt to the condition of sustainable development. And the main challenge of the enterprises in this type of dynamic environment is to balance the relationship between economic benefits and environmental responsibility, and ultimately to achieve the strategic goals of sustainable development, also taking into account social requirements. And therefore, it is important to adjust the given business operations and their size to the existing environmental conditions, and to rationally manage natural resources and produce products that in the way does not threaten the environment and society, and at the same time ensure that we achieve a competitive advantage. And the dynamic capacity for sustainable development refers to the ability of enterprises to sense, acquire, or reconstruct internal but also external resources, including ecological and technological resources, to cope with changing business environment, and through the dependence and creation new organizational resources and strategic practices. And these capacities actively supports the circular strategies and eco-innovation practices in turbulent business environments, and are one of the sources of competitive advantage for enterprises. And in order to achieve a long-term effect of sustainable development, enterprises, especially in bioeconomy sector, undertake actions resulting from the entrepreneurship, with translating to the search for new solutions and the creation of innovation or new values in the economic and social and also environmental dimensions, apart only from solving existing problems. And one of the driving forces of innovation was this sustainable development. And researchers in the literature and scientific often argued that there is no alternative to sustainability, and this principle has changed the companies to develop products and services for new clean technology markets, to provide better control over the life cycle of products and services, for use of material recycled to increase the efficiency and improve the quality of product life. And also, it must be stressed that increased consumption and the huge number of new products which appear on the market, when we combine it with reduced life product life, and it translates into the increased consumption of new raw materials and energy and more solid waste generated by agglomerations and other residential areas. And it's also imposed a challenge in innovation design. The challenge is the impact stage, which is often overlooked in the innovation research, as the innovation is considered ready when it's implemented. And innovation can be an economic success, but also a social disaster because of its impact on the social practices. So according to research carried out under the social economic consequences of the fourth industrial revolution, it is sustainable development, industrial ecology and eco-efficiency that guide the development of the next generation of raw materials and production technologies. Also, in addition, the results indicates that the life cycle assessment of products is a key tool providing information necessary for the environmental monitoring and assessment, as well as in the decision-making processes. So in this case, the assessment of different scenarios helps managers to consider the alternative options for improving the environment and allows to assess the impact of both the process and the end product. And in this way, it can be streamlined, the management process, it can be streamlined, and the operation and implementation of greener innovation can be imposed. And in response to the environmental and social economic challenges, the corporate strategies play an important role in building a competitive advantage. As some researchers argue that sustainable development strategies have an impact on competitive advantage through the use of more efficient processes, also because of increased productivity, lower costs, and new market opportunities. In order to meet the eco-innovation challenges, eco-innovation plays an important role. It is necessary to mention that here's the factors specific to a given company, which results from both technological development and the current state of development, market position, or the level of technology advancement. The enterprises from the bioeconomy sector strive to plan and implement strategies for the sustainable development of the company, and the strategies are based on the assessment of the company's potential and the innovative potential, and on the analysis of the company's external environment in terms of possibility of the innovation implementation in the decision-making process. Moreover, on the basis of the general and specific factors, the most favorable strategies for enterprises from the bioeconomy sector were also identified, and the research indicates that the most advantageous strategy undertaken by the enterprises in the bioeconomy sector is the innovative and offensive strategy. And also results confirmed that companies from the bioeconomy sector are also recognized as innovative. And within the framework, 5 core factors are specified. Factors for developing innovation, sustainable innovation, economic and financial, market and technological, ecological, organization and human resources, and legal. And finding revealed that the most significant factors are economic and financial, and market factors that determine the choice of innovative and offensive strategies by bioeconomy enterprises. Also, the main challenge for enterprises is to undertake as well as said also Ariel, the innovative solutions, as to proceed with development of new products or production methods, taking into account not only economic, but also environmental and social goals. Due to the limited time, I'm strongly encourage you to get familiar with the works and papers that stemmed from the research. And thank you for your time and for your attention.
Thank you very much, Szymon, for this great presentation. We will move now to the last speaker, Małgorzata Smol from Polish Academy of Sciences, Mineral and Energy Economy Research Institute is not available, but her presentation is available online. So please welcome with me Dr. Małgorzata Pink of Agriculture University in Poland, and she will be talking about new developments made by her university. So Gosia, please, the floor is yours.
So thank you for having me, Maciek. I'm very grateful, and I would like today to present like a short introduction of the latest developments in the sector of bioeconomy. I want to show them in the context of value chain. And I basically want to present some of the inventions of University of Agriculture's that our colleagues are developing. So I said I want to show them in the context of value chain, so let's define it at the beginning. I understand it, understanding it classically, like Michael Potter, it's a set of activities that an operating agent perform in order to deliver a valuable product to the market. But we cannot really understand it in this way when we talk about bioeconomy, because bioeconomy requires like a multiple actors to cooperate, and it actually requires some sort of like an interpenetration in the value chain of the individual product. So it can give us this effect of circularity we've been talking about today already. So in this context, I'll introduce you to some of the products, the inventions of the researchers, which do fit this idea of circular model of bioeconomy. It creates the value of the product itself, but also is using the value from the side streams, and it is adding to the value chain of other goods. I will present you the side streams from slaughterhouse, from marine and aquaculture sector. So the first project is entitled EcoFeather, EcoPuro. And it is actually not bioplastic for once. It is non-woven textile made by a consortium of 4 partners. And from the University of Agriculture, it was Dr. Piotr Kacorzyk who was the project manager. This consortium used the side stream from poultry slaughterhouse, the feathers, which usually is quite complicated to deal with when you want to make a utilization of it. And out of the fragmented feathers, they basically created a non-woven textile, which you can see in the right bottom corner of my screen. This material was to help to solve 2 problems. First was turfing difficult surfaces like flood embankments or roadsides or mounds or created by human slopes. And with this kind of soil construction, it can be difficult to maintain them. The soil is settling, it erodes easily with wind and water, and the seeds of the plants that are supposed to hold the ground with the roots, they basically being washed away. They drying out or being burned by sun. You can use like a cement or plastic truss, but this is really limiting bioactive space, and it's also not a very low emission solution. So with this agro textiles, what they managed to do was solve this problem. And another problem, which is like a kind of a side effect, they also developed a way to conserve the snow piles for the ski industry. The winters are shorter and shorter, so it appeared to be quite useful. So you can see here this feather material. It helped to solve both the problems, both the issues. Here, what you see, it's a slope. It was protected by the agrotextile. The material doesn't have to be removed because it's fully biodegradable and it is decomposing. Once it's decomposing, is actually fertilizing also the plants that are creating this turfing. And here you can see the snow piles. They were being formed in March, beginning of March. They survived all right until end of April, so it worked as well. So this product, this non-woven textile, it has all possible qualities. It's biodegradable. It's using a side stream. After decomposing, it's actually enforcing the growth of the plants. It facilitates seedlings. It has big water capacity, so it protects from floods and also assure that there is the reservoir of water for the seeds. It works a little bit like albedo and protects the seeds from to strong sun, and it is cheap. So this product is actually already being in the process of introduction to the market. But next one, it is yet not monetized. It was created by a team of Dr. Ewelina Jamrus, and it is biodegradable, active, intelligent food packaging solution. She wanted, together with her team, to solve 3 problems. First of all, reduce food waste and plastic waste from the packaging. She also wanted to develop the product that would extend the life of the food product on the shelf. So basically you could eat it longer. And finally, an issue to understand when the food is still edible. We often have a problem if actually something could be still eaten or not. So how she approached the solving these problems, she created a bio-based film, bio-based on the seaweed, Furcellaria, which you can see here in the corner. And she enriched it with extracts of certain substances in majority of a bio origin. This way she received these active, intelligent films. Some of the examples that are most interesting, the film with yerba mate extract managed to extend the life of the soft white cheese by 7 days. She also wanted to use a side stream to get involved in the circularity. She used the side stream from aquaculture. Specifically, it was a carp skin. She got gelatin hydrolysate out of it, which added to the film, extended the freshness of smoked mackerel by 7 days and limited oxidation of the fats by 22%. The other direction was those intelligent films that would inform us if the food is still edible. So she added all kinds of teas, green tea, white tea extracts, and they actually have potential to indicate the changes in the freshness of the food by changing their own color. And these products are still on the base where they're not introduced to the market. They're still waiting for possible development. And finally, I want to show you and introduce you to the invention of Gohar Kachetarian and her team. What she's doing are so-called bio-nanomaterials, and she wants to use them in food. She already used them in the cosmetic sector, and also she proposed to use them in the medical sector. The problems she tried to solve, and obviously with her people, is first of all, efficient use of active substances like, for example, essential oils. She also aimed to limit waste, create a packaging for food and for other industries, and to create bacteriostatic and germicidal material for medical use. As a base for her films, she actually used a side stream from biomass from the sea, the marine biomass. It was chitosan, sourced from shrimps' shells. The shrimps were kept not to make chitosan, they were kept to make food, and otherwise it would have to be burned. The material is biocompatible, it's biodegradable, so it has a lot of qualities. And this product was enriched with nanocapsules of essential oils. Particularly, they managed to prove that the clove and thyme oils are very useful. And it has to be said that the method of encapsulation is also own work of team. So adding these essential oils, the thyme and clove, they elaborated the material which is antibacterial. So like in case of Dr. Jamrus, it extends the food freshness. It's also fairly cheap. And it also can be used to create fully biodegradable medical dressings. With the mentioned oils, they are inhibiting multiplication of E. coli. They are inhibiting multiplication of Staphylococcus bacteria. So this is something that potentially would have good use in the medical sector. Then part of her research was actually already adopted by the cosmetic sector. She used also Hitosan-based products, that mix them with the glycerin and achieve the gel. With active nanocapsules, it creates efficient cosmetic, which you can see here to care for your skin. As a side product, actually, they were made for Scandia. That was like Together project. As a side product, she also achieved this biodegradable film for packaging the bath bombs, and they are wrapped with the kind of solving film, which afterwards creates a body mask, which enriches the skin. So, excuse me. Part of these products are still not monetized. They're still waiting for entry to market, like the films, like the medical use of the solution. Thank you very much, and well, if anyone would have questions, please go ahead.
Thank you very much, Gosia. That was really interesting presentation of the products, bioproducts within the circular economy. And I think this is now time for the discussion. We've got some 15 minutes. If anyone from the presenters would like to join, also welcome. But I think we'll start here with the rubber issue as we started to discussing it. Our director for science from Jerzy Haber Instytutem Katalizy and Fizykochemii surface chemistry,
Polish Academy of Sciences.
Maciej, please comment on that.
Yes, I would like to point out that we have fantastic overview from Alexander about potential technologies, how we can recycle rubber material. So actually that we really can close the loop technologically, that we actually really are there. So that there are technologies recognized, but there is also a very important problem of changing our economic culture, because at the moment we are just kind of in a deadlock between producers and the consumers, and producers actually are so focused on actually making profit out of the producing the tires, and they are not taking responsibility for the end point of this loop. So actually we have to think about how to convince policymakers that these producers are actually responsible for bringing back the tires back to the lab or back to the processing facilities, which could actually really make this material truly circular in terms of closing the loop. So this is something which already happens in Europe. You think about, for example, what Michelin is making, that actually they are basically lending the tires to the transportation industry and then repurposing them back just by making the new tires from what they already sold. But this is actually only an exception. And normally the customer, I mean, if you go with your car, change for the winter tires, and the company says, which I mean, the car service says they are too old, they are just selling you a new one and taking them to the waste. And the producer has no contact with this tire. So this is something which we really need to address, and we really need to change this, how the way we are thinking about it, and there should be a social push for this.
Isn't it the problem of the education that we have in place in many different European countries, that there is lack of understanding from the younger generations the importance of the circular economy for example of the rubber that you mentioned?
Yeah, I mean, we had some indication of this. As first of all, people are not aware that they are bioeconomy. So the companies are not aware that they are really doing bioeconomy. But I think that the problem is more general. People actually do not have a feeling what bioeconomy is and what is the general concept of it. I think that we have quite a good understanding in the society of recycling as such, but the idea how it is taught to kids, and they really do matter in terms of our future, of our civilization, is completely wrong. I have hands-on experience about it because I still have a child at school. And you know how actually recycling is taught to kids? They are asked to buy materials and make costumes out of the well, recyclable resources, but they have to bring the folies, they have to bring toilet paper, and then they make something, and then it goes to waste. And this is really ridiculous. This is something which is completely stupid. And this is the way we are teaching kids that something which is fundamentally wrong, that you go for the goal fast and dirty. That's actually how the linear economy works. We are so focused on making well, basically products fast and dirty way, not the sustainable slow way. So actually the good thing would be you have to collect the materials, not on tomorrow, but in a sustainable, extended way, and then make something out of it, which is not really going then for the waste. And this is something which we should address on a very basic level. And I think there is a lot of work for us to do.
I believe so. For example, with Yasmina, we are preparing different Horizons projects, and always in those projects we have an aspect of the soft science, in a sense that we would like to develop schemes for recycling of novel packaging material, which are bio-based and biodegradable. But on the other hand, when we talk to people from cities, from municipal agencies, they see the lack of understanding within their own bodies. So I believe the education on different levels is very important in order to provide for the circular economy to come to existence on a real life basis. I think we can go to another part, if you don't have any more comments, Kazimierz, for the circular economy we are talking here about and bioeconomy.
No, maybe one more thing worth to add, that I agree that that's with Professor, that this is something which is actually not being very popular, and we are in the beginning of this path. But there is something that people start to think about how we can make it better, but it's most important to acknowledge that we per se, as on average, we don't understand we are in bioeconomy. We are working in bioeconomy. Recently, when we are working in the special interest group bioeconomy, and we try to discuss this issue amongst the many companies in Małopolska, we couldn't actually convince them that whatever they do, they always at least touch the bioeconomy, because they have suppliers, because they produce waste, because of many things. And
true, yeah.
unless we'll convince all these people, all these businesses that this is actually at least circular, not bio.
But that's an issue for over the past years, like at least 5 years that we are talking about that. Do you see any progress?
Very little.
Very little.
if I may say so. This year, during LifeScience Open Space, we have more, I would say, knowledgeable presentations about that issue, which makes maybe some kind of sign, gives some kind of sign that this is a kind of progress. Mm-hmm. But this is still something we have to focus on. We did have recently a lot of workshops on that, and there is some kind of understanding and interest about that, but still, you know,
it's from academia point of view, not regular users or producers.
I don't agree with you. I mean, you remember the experiment with which actually Krakow City did with the automatic machines for taking back bottles. It was so popular that they had to close it down.
Yeah, because it was too expensive for them.
It was too expensive. But I mean, this means that actually people are aware. I mean, in Germany, when you go and buy a bottle in plastic bottle with water, you pay the fund, right? So the caution for this, and you have to give back the bottle. I mean, at least you are encouraged to, right? When if you are in the airport, you will most probably throw it away, but there will be a guy who will be collecting this and then making a profit out of it. Yep. I mean, what is the problem? I mean, people actually are ready, at least in the big cities in Poland, to really do this.
Yes, exactly.
I mean, it was proven by the experiment. So it's not like that we are not ready for this.
And actually, it was too expensive for the city, but it wasn't too expensive for the environment and
Yes.
for the whole system.
I mean, it was an experiment which was actually ill-defined in the basic because actually it was funded by the city. But if people were paying for this in the price of the water in the first place, then we'll be just getting it back. From that's only the cost of organizing this in the collection center, and then some companies which will actually really do the repurposing of the plastic. But I mean, this is actually for polyethylene. The technology is already there, I think, for 20 years.
And another thing, what I wanted to point out from presentation of a professor and what was also highlighted by you, there are technologies already. So we have technologies, we know how to do it. The only problem is how to integrate them, how to make use of them, not to develop something very, very new. So of course it will come and it will be necessary, but the biggest challenge right now is actually how to make use of those, of the knowledge we have.
Yeah, how to implement, like Jasmina was saying about PHA packaging, nanocellulose. Gosia was saying about developments from Agri-Uni in Kraków. So, for example, those mats that can be used for storage of snow or preventing the soil leakage. And those are achievable by the, taking by the hand from the market, but to convince people it's hard. So I think the education and promotion of those developments is important.
I think we need some kind of examples, the companies which first will pick up something and make money on the developing or introducing the new business models. But I had another question to Professor that was interesting, because we are in the age of digitalization. Can digitalization help to improve those processes, to introduce those to the companies? Will do they have to first be digitized, transfer their business model to digital domain before they start making use of circular economy, etc.?
I'm not that optimistic regarding this point. I think costs and finances are often a much better pressure. As Maciej mentioned it, in Germany you have to pay a deposit for each bottle or for each can. And I think, if I remember correctly, in Germany you have to pay 20 or 25 euro cent per bottle to return it. And that's a very high pressure for the people to collect these and to return this to the shop. And of course, these drinking bottles are not used as a drinking bottle again. They are shredded, but the material is recycled for various purposes. And this can be applied, I think, also for many other materials, at least bulk materials which are used in large amounts in the households. And I think there must be also some pressure to the companies to behave in a different way and to force these measures. And this can be done, I think. There are several examples, successful examples for this in the past. But if the politicians are so weak, not strong enough to force the industry and the traders to behave different, they of course will, in most cases, go the easiest way, the cheapest way.
That's the world works.
Yeah, yeah. And I think this must be changed dramatically. And one other point which has to be changed, and I'm not sure whether the European Union alone will be successful, but it could be one strong unit. They all must behave similar. Otherwise, they will go to a different country or to a different region, or we will be swamped by materials produced in Asia and so on. So let's say the economic pressure must be the same all over the world. Otherwise, it will not function. So a small Poland or a small Germany cannot reach very much.
Which doesn't mean it shouldn't try.
Yeah. Okay, we can be a Vorbild, we can be a good example for others, but if the economic pressure is very high, such a good example will probably not work alone.
That's very nice words to sum up the first session of our session today. And now we can move actually to the examples of bioeconomical developments started by Gosia Ping in the beginning. And we will move now to Ms. Gabriela Dignot from Oil and Gas Institute, National Research Institute, and she will be talking about sustainable energy production. So please, the floor is yours. We cannot hear you.
Okay, I'm sorry, I was on mute. Thank you so much for a great introduction and a great session for today's discussion. So please give me 1 second to share my screen. Good morning, everyone, once again. My name is Gabriela Dignot, and as you previously said, I'm working in the Oil and Gas Institute, the National Research Institute in Krakow, located in Poland. So my goal for today is to tell you in general about the sustainable energy production, and in case of the certification of this sustainability, about the KZR Index system. So my today's brief presentation, because we don't have so much time, so I will shortly tell you in general, and I would like to cover an overview for a catchy recent times topic about the sustainability of energy production, starting from the climate targets to achieve European Union rules, and especially about the KZR Index system, which allows to confirm that sustainability. So let's move on. European Union energy policy and its obligation to and its objectives in terms of energy neutrality are increasing. The European Parliament's Fit for 55 document called Fit for 55 package, which updates the previously issued European Green Deal, specifies that by the 2030, the reduction of the carbon dioxide, the reduction is to reach 55% in accordance to the year 1990. And by the 2050 to reach climate neutrality. As you can see, we are here now with the reduction targets. So there is a lot to do for each of European country to fulfill the European Union policy in terms of GHG, I mean greenhouse gases reduction, and climate neutrality. In order to achieve these targets, it is important to move away from fossil fuels to renewable energy sources. In order to confirm a realization of these goals in the area of energy, the renewable sources included in the RED II directive, it's here the puzzle, the one of the puzzle that we should fulfill. It's necessary, among other things, to confirm that the compliance of the biofuel, bioliquid, and fuel from biomass in all supply chain, and also the energy and electricity production, biogas, etc. So it is important to confirm that they meet sustainability criteria and meet the reduction of the GHG emissions. Confirmation of compliance with sustainability takes place through voluntary schemes in accordance with this renewable energy directive, and such one of this voluntary scheme is our KZR Index system. which provides procedures and defines requirements in the aspect of activities which entity should undertake adequate to the requirements of the European Commission. So in general, our system gives economic operators the opportunity to demonstrate that they meet sustainability criteria as required in the directive called RED II, which was issued the 1st of July this year. The KZR Index system is a global and first and only voluntary scheme developed in Poland that confirms compliance with the sustainability criteria defined in this directive RED II, and previously in the first edition of this directive, RED I. The system is owned by Oil and Gas Institute, and the Oil and Gas Institute is also the administrator of the system. Global reach of the system means that any interpreter to the supply chain of biofuels, bioliquids, and biomass fuel can be certified regardless the place of the supply. What do we certify? The subject of certification in our system is the whole pathway chain of biofuels, bioliquid production, as well as of solid fuels product, for example, heat, cool, and energy. So all the pathway of the production, starting from the place of origin and to the final user. The entire supply chain must prove that the biomass is compliant and meets the sustainable criteria. In order to demonstrate the confirmation of its sustainability of the goods, participants of the system in the supply chain are subject to audit. Verification is carried out by independent certification bodies accredited by our scheme. Of course, each interpreter is audited individually and receives its own certificate. Okay, let's go to some details on our system. So we cooperate with actual 8 reputable certification bodies. Those will be listed on the next slide. We have issued over 2,500 certificates which are published on our website. We also are registered in the BLI, which enables to export of the products to Germany market. We cooperate with leading companies. I listed some of them, which I thought you may know. As you can see, they act in a diverse fields of industries, biofuels, biocomponents production, for example, Bioagra produce bioethanol, farms, oil production, paper production, furniture industry, and heat and power production. So what distinguishes us? First of all, we are really reliable. It means that we ensure a uniform, objective, and reliable auditing and certification process carried by approved certification bodies here. We recommend adjusting our requirements to existing management system as warehousing, finance, and accounting. We quickly respond for needs and questions of customers, including the possibility of preparing individual training. We cooperate with other accepted voluntary schemes by European Commission. We have a communication platform, interactive, and additional verification tool is certified entities. And it contains information on issued and suspended certificates with reliable entities with a global reach. Of course, we have competitive prices Of course, it is available on our website. And what's more, what's interesting, in 2020, over 900% of our participants once again received our certificates, so they still are with us. There you can see a screenshot of our website. So before joining our system, you have to meet beside formal criteria, for example, registration and agreement, the substantive aspects. So we have like 11 documents that you have to implement into your internal procedures to meet our requirements. This is the path for the registration. It is already published on our website. So a registration form, then you have to fulfill all the substances and formal criteria, go to the audit, sign an agreement with the certification body, then you will receive a certificate and you will become our participant. And you can sell, of course, sustainable products. Thank you for your attention. It was a short brief. There is not so much time, so to be on time, I would like to thank you once again. And if you have any questions regarding the certification process, our system, joining our system, confirming sustainable criteria, do not hesitate and contact me. Thank you so much.
Thank you very much, Gabriela, for this great presentation and the certification possibilities that your institute provides. And now let's move to another speaker. Again, I would like to welcome Professor Szaleniec from Instytutem Katalizy and Surface Chemistry, Polish Academy of Science. And Maciej will be talking today about energy, but on a smaller level, NADH production, biocatalytically, and aldehyde productions also. So floor is yours.
To be more precise, I'll be talking about how to actually link hydrogen production and the actual utilization of hydrogen with synthesis of value-added chemicals. As you have heard from Jasmina in today's morning session, pharmaceutical production can actually produce lots of waste, even if it uses biocatalytical method. So here I would like to present you with some solutions for this actually, to how we can address this problem. First of all, the object of this short presentation is kind of an unusual enzyme, tungsten aldehyde oxidoreductase. This is the kind of enzyme which has the tungsten cofactor in its active site, and normally it comes from bacteria. It oxidizes aldehydes. This oxidation in a cell is linked to NAD reduction, but outside of the cell can be linked to other artificial compounds which can reoxidize the enzyme. We have unusual recombinant system. So this is a very important thing for potential application of this enzyme in industry. This is unusual enzyme and also has a bit unusual host for production, aromathalloum vansi. This is the special strain which is a close relative to the native bacterium which we found the enzyme in. And it's able to produce, but the bottom line of this is that we can actually produce a lot of this enzyme, and it can be deployed and in a wholesale system for your production. So in case you wanted to apply this, you can join it with another recombinant enzymes inside aromathalloum vansi. Normally the enzyme is oxidizing aldehydes, and it has a very broad spectrum: aliphatic, aromatic, heterocyclic aldehydes, which are selectively oxidized to carboxylic acid. This is actually not the topic or the scope of my topic, because we realized that the enzyme has additional very interesting activity, and it turned out to be new type of hydrogenase, tungsten hydrogenase, and this is actually the first example of such hydrogenase in the world, and it's able to reduce acid to aldehydes using hydrogen. So this is actually a possibility to linking the hydrogen technology to synthesis of various materials, because you can use hydrogen to reduce tungsten cofactor, and then using this stored energy, you can reduce acids to aldehydes. This is first application. So if you want to selectively reduce acid to aldehydes, and this is not really easy in terms of chemical approach. It is really something which is very difficult to make by chemical means. Usually you end up with alcohols. Another possibility is to use the same hydrogen to reduce this tungsten cofactor, and then using chain of iron sulfur cluster and FAD cofactor, you can normally reduce NAD to NADH. And this is another application. You can use the link, basically, hydrogen oxidation to NAD reduction. Both processes are possible with this enzyme, and they have different optima for pH. So we can actually steer with this based on pH of the situation. So the first application here, we have shown that that you can basically reduce aliphatic, aromatic, or heterocyclic carboxylic acid with hydrogen to the respective aldehydes. And here you have presentation of another application, so NADH regeneration system. As you know, in biotechnological applications, NAD or NADH dependent enzymes are very widespread, and NADH is quite expensive compound. It has to be recycled. So here's a proof of principle. We hooked this enzyme IOR to the industrially implemented already the alcohol dehydrogenase from Aromatolum aromaticum. This enzyme is used by BASF, and we reduced acetophenone to R-phenylethanol, also valuable synthon for synthesis of chemicals. We're using the IOR as a hydrogen-dependent NADH recycling system. As you can see here, for 2 days, the process was linearly proceeding without any hiccups. So it's kind of a proof of principle it can be done. Another possibility is to use a cascade, and from carboxylic acid, you can use you can construct a cascade of 2 enzymes, IOR reducing carboxylic acid with hydrogen to aldehyde, and then specialized aldehyde dehydrogenase, and then that way you can make an alcohol. And in here, this dehydrogenase is also NADH dependent, so IR is actually supplying NADH, and that way you have the very clean system, which actually puts all the hydrogens from the gas on the molecule. There is no waste out of it. Of course, you can imagine different types of cascades here. For example, aldyl condensation can be done by aldolases or any other enzymes which uses aldehydes as a substrate to convert to some kind of valuable compound, and also utilizes NADH as a source, as a co-substrate of reducing agents. So we have at the moment cell-free system enzymes in vitro. As you can see from this graph, there is quick stabilization of benzaldehyde, so the enzymes actually very quickly producing this aldehydes. Well, potential cascades can be designed in a multiple way. We have shown that you can use also syngas as a source of hydrogen. This is not a very green source, but at the moment this technology for the syngas, of course, is already there. So we can show that the other components of syngas are not killing the enzyme. This is important in terms of application. So basically, market potential of this, you can use it for aldehyde reduction, so manufacturing of different flavoring compounds, biofuels from alcohol, via aldehydes to alcohols, or direct substrate synthesis, which you need to hook up for different next steps of the synthesis. Also, you can use it as an NADH recycling system. During fermentation process, it can be coupled to any NADH dependent process. And of course, the idea for in frame of bioeconomy is to actually fuel this with a green hydrogen. So something you can use from sustainable energy source, water electrolysis, and then that way you have basically reducing agents for free in terms of well, basically the overall cycle of your process. So in summary, we have new type of enzymatic activity here, which is expressed in bacteria, potential pathway to aldehydes. Due to thermodynamic reasons, cascade solutions are much more sensible, and deployment of this system in wholesale is possible. And clean NADH recycling system with not producing any waste in your reactor. We, at the moment, have a few months ago filed 2 patents for these technologies, and we are looking for companies that will be interested in co-development of this technology to the industrial level. So basically, evolution of this enzyme towards higher activity or substrate specificity, development of efficient wholesale system cascades for desired product, and also joint patenting outside of Poland or potentially licensing of this method for application in the company. And if you have any questions, please contact me directly. Thank you a lot for your attention.
Thank you very much, Maciej, for this great presentation on providing new blocks for bioeconomies and for circular economy on a little scale, but which can bring a lot of money in future.
Kind of a link between what's actually our biorefinery in Orlen Południe is making, right? So hydrogen production, and then you can link it up to production of chemicals.
Exactly. When we are talking about chemicals, let's move a few blocks away from us to Kraków University of Technology and welcome Dr. Szczepan Bednarz, who will be talking about undiscovered potential of fatty acids, carboxylic acids. So Szczepan, the floor is yours. And
good morning, everyone. So once again, thank you for invitation and for a kind introduction. And I will continue a little bit story about carboxylic acids because I represent a group of two research group now today, and I'm going to talk about our investigations deal with selected natural carboxylic acid, itaconic and citric acid. I'm working at Kraków University of Technology at Faculty of Chemical Engineering and Technology. And yeah, these acids are examples of platform chemicals. And as we know, the term platform chemicals is strongly connected with white biotechnology. And white biotechnology is applied branch of biotechnology used by industry on industrial scale, and this industry is used enzymes or living organisms for transformation of chemicals or food or organic wastes into desired products. And so basically, our research is on the border of white biotechnology. We are chemists, and we are looking for new methods of transformation of bioproducts. As I mentioned, we focus on carboxylic acids, citric and itaconic, and we are thinking how to put more value to these simply molecules and how to transform these compounds into more advanced value-added products. On the left side, you could see a list of examples of bioproducts. And generally, we have two groups of bioproducts. The first group is, for example, vitamins or drugs. These molecules are more complex and more expensive, and they could be sold on the market as a final product. And on the other hand, we have also quite simple molecules like glycerol or amino acids or carboxylic acids, which are much more simple molecules and rather cheap, and there is a general need for transformation of such platform chemicals such metabolism products for valorization of these materials and for transformation of these compounds into value-added products useful for different kind of industry or economy. On the right side, you could see molecular structure of citric and itaconic acid. These acids are well-known biomonomers because they have at least 2 carboxylic groups. So this acid could forms biopolymers, polyesters. And also in the case of itaconic acid, it is possible to form macromolecules using radical processes because of the double bond between 2 carbons here. In the case of citric acid, there is a quite interesting and waiting for discovery chemistry of chemical reactions of the acid under high temperature. It is a subject of the study of the second group of the group of Viktor Kasprzyk, and they are working on chemistry of high temperature reactions of citric acid. It seems that the acid is able to form with also quite simply synthetic or natural molecules, wide range of fluorescent molecules. The final step of pyrolysis of citric acid are carbon dots. You probably hear about it. These materials are poorly investigated. We don't know the exact chemical structure, and this acid, citric acid, is a precursor for starting synthesis of such materials. Okay, now I'm going to tell you briefly about our team. We are focusing on itaconic acid chemistry, and now we are implementing a project with partners from Czech Republic, from Institute of Macromolecular Chemistry, and we are thinking how to convert itaconic acid and next the polyitaconic acid into new hydrogels. And in contrast to rubber, for example, our hydrogels are not chemically linked, but physically linked. And the nanogels have a quite strong affinity for metal cations or for some dyes. So we see possible application for such materials in for example, wastewater treatment. Another our recent discovery is finding that the natural itaconic acid it's possible to polymerize this acid using just sunlight without using of toxic photoinitiators. So it is something which we just published in our recent paper, and it opens new way for conversion of such acid into polymeric materials. If you are interested in this subject, please have a look into the papers listed here. Now I'm switching for the citric acid story, and in this subject we have also some number of papers regarding to synthesis of fluorescent dyes using citric acid as one of substrate. We know how to modify polyesters or synthetic petrochemical materials to give them some strong blue fluorescence. And also Victor with his team is working on a novel analytical protocol using citric acid to detect and to quantify some important synthetic or natural products via condensation with the acid. Okay, summing up, we are ready and open for cooperation. We both with scientists from universities or with partners from industry. Here you have here you have our emails. So if you have any questions, please don't hesitate to contact us. And at the end, I would like to thank Polish and Czech national agencies for financial support, and of course of all you for kind attention. Thank you very much.
Thank you very much, Stefan, for this nice presentation and introduction of the possibilities for collaboration with your teams, yours and Victor's. So I think it's time for the last presentation. We've been in Belgrade, we've been in Kraków, so let's move to Dublin in Ireland and welcome Tania Narancic. She's employed at University College Dublin, and she will be talking about her project, Biosorbic. Tania, floor is yours.
Thanks, Maciek. Just give me a second here to see, because I have two screens, obviously. Why not? So just to make sure that I will be sharing the right screen. Now, can you tell me, do you see my presentation? Perfect.
Yes.
Thank you very much. Thank you, Maciek. So thank you for your kind introduction. As Maciek said, I am located in Dublin, in Ireland. I am affiliated with University College Dublin and Biosorbic. And just to briefly say that my background and my research focuses on the metabolic engineering and design of microbial biocatalysts for the conversion of various feedstocks into valuable compounds. And today what I want to do is present Biosorbic and our activities in Biosorbic. So brief overview, Biosorbic is Ireland's National Bioeconomy Research Centre. It was established in October 2017 by funding institutions, academic partners. In addition to UCD, we have three other universities, University of Limerick, Trinity College Dublin, National University of Galway, and Agriculture and Food Development Authority, Teagasc. Researchers from these institutions came together way before 2017 and recognized that we need to do something and that we need to act in order to allow just transition of Ireland into more sustainable society. Today, Biosorbic counts over 120 researchers that are doing just that, allowing the transition and supporting the transition to more sustainable society. In addition to our academic partners, Biosorbic's community involves many industrial partners, and our community is growing pretty much on a daily level. And here you can see some of our partners, which are, for example, major dairy companies in Ireland, Glanbia and Carberry. We're closely collaborating with mushroom producers, cooperative mushroom producers, and Monaghan mushrooms. We're also closely working with many companies that are looking to extract value from marine resources. So how do we do this? Biosorbic's activities could be divided into platform projects, and I will explain now what that is. So those are principal investigator-led projects where we have activities that could be separated into three different areas. But as you will see during my talk today, we are actually working together and bringing all these expertise together. Selective separation platform is a platform where we have many researchers that are working together on accessing valuable molecules that are present in a complex mixtures, such as waste streams or side streams from various industries, as for example, dairy industry. And they're developing advanced materials and membranes that allow us to do filtration on nanoscopic levels to extract valuable molecules such as sugars or proteins or carbon dioxide that are present in these complex mixtures. Conversion platform relies on the use of chemical and biological tools in order to convert either these extracted molecules, if we're looking at more pure application, or we're directly working with various feedstocks and looking to convert them into platform chemicals, novel chemicals. For example, we are working on designing biocatalysts for the conversion of dairy industry side streams into valuable platform chemicals, or our chemistry partners are designing vaccines based on sugars that are extracted from these complex waste streams, or molecules that are used for targeted delivery of drugs. And then we have our sustainability platform that is focusing on analyzing socioeconomic aspect, biodiversity, natural capital, consumer and citizen understanding of the bioeconomy, societal engagement, life cycle thinking, and the bioeconomy policy landscape. Because as we know, we can't just design bioprocesses or processes without looking how could that affect the currently present products on the market or the processes that are currently existing. And as I said, we're working very closely with our industrial partners. So we do that through so-called targeted projects. So what we do, as I said, one of our aims is to deliver market-ready and scalable products on the market. So we are working closely with our industrial partners, firstly, to define specific challenges. And then we offer to them research and development facilities in our labs, and we're providing leading edge solutions to these specific challenges. At the same time, we offer the analysis of market credibility for the new technology, process, or product. We are a national bioeconomy research center, but we're always interested in expanding our collaboration internationally. So we are involved in many international projects, and here I will just briefly mention two that are both funded by Horizon 2020. One of them is EU-China partnership, and that's a project named Mix-Up, where we're focusing on providing sustainable, novel solutions to convert mixed plastic waste into biodegradable polymers and valuable chemicals. And Uplift is another H2020 funded project where we're specifically focusing on post-consumer packaging material, and we're looking at novel means that could be added to currently existing recycling schemes that would allow us to recycle and upcycle packaging materials. We also have so-called flagship projects, and I will briefly introduce a couple of them, where we have intense collaboration among many researchers that are present in the center. For example, Farm Zero C is big collaboration between Bioorbic and Carberry, which is one of the big dairy companies located in the west of Ireland. And we involve many other partners, including farmers themselves. And Farm Zero C is focusing on net reduction of greenhouse gas emission by having a holistic view of a farm, so to reduce greenhouse gas emission, at the same time to increase the health and the resilience of the farm. Now, what I want to talk to you in more detail is Next Gen Wood, which is one of the flagship projects, and it is looking to improve the forestry sector in Ireland. When you look at the forestry sector, in basis, it is a success story. It contributes with 2.6 billion euro to the Irish economy. It creates 12,000 jobs in forestry and wood processing sector. Ireland is aiming to position itself as a leader in climate action. And Ireland is, I think, the first country that has actually signed climate action into law this year. And therefore, Ireland is committing itself to net zero carbon emission by 2050. And one of the means to do so, the strategy behind that is to either balance the production of greenhouse gas emission or to overcome it in net by planting more trees. And Ireland has set to plant about 22 million trees a year, which is quite an ambitious goal. We are behind it at the moment, but hopefully we as Bioorbic and our activities are going to help this. So There are some challenges that are coming with this. While good side of planting more trees is obviously going to contribute to afforestation level, which is currently at 11% in comparison to 33% in the EU, so very low average. This is going to significantly change the way we're using farming land. Ireland's forestry sector is relying on quite traditional processes for the wood processing, which means that it generates a lot of waste material and it generates low value products. Another issue is that climate, because climate in Ireland the way it is, it allows fast growth of trees, which provides trees that are of poor quality. So we have quite low return to the economy as opposed to what we could return in forestry sector. And investment into this sector was quite low until now, and it lags behind other countries that have quite strong forestry sector. So in the conversations with Department of Agriculture, Forestry and Marine, Enterprise Ireland and Quilche, which is state-owned commercial forestry business, we came up with the idea to change the view we're looking at biomass, lignocellulosic biomass, and how can we generate novel processes to process this biomass and use it both as material and as feedstock. So NextGen Wood is essentially an ecosystem that involves Bioorbic researchers, but also Amber researchers. Amber is another national research center that has extensive advanced material expertise. And in Bioorbic, we're going to draw on our expertise from a conversion platform, but also sustainability platform. And we also involve a lot of companies that span from small producers, farmers, forestry owners, product manufacturers, etc. And what we aim to do is develop higher value wood derived products to generate innovative wood-based materials and biochemicals, and at the same time to train and develop a future skilled workforce, which we think is very important for transitioning to bioeconomy, and obviously to translate research to industry and accelerate industry transition to a carbon neutral economy. So our specific aims in these projects are to improve wood products by expanding the portfolio of products, to valorize lignin, which as we know is quite a tricky material to work with, but we are going to develop bio and chemical conversion of lignin to platform chemicals, also to use it as a feedstock to produce protein-rich cells, to use sugar derived from biomass as prebiotics, and to produce high-grade carbon fibers derived from wood. And obviously, as I said, a very important aspect is to use life cycle assessment, and this analysis will cross-cut each of the tasks that we're specifically looking to do. And finally, I will wrap up by just mentioning that, as I said, one of the goals of Orbic is to produce specific skilled workforce that will allow the transition of industry towards bioeconomy. And one of the projects that we are involved in is again funded by Horizon 2020, and it's Talent for BBI Marie Curie action. And I just want to mention that we will have opening for 11 early stage researchers, so PhD positions, and these researchers will be working closely with a specific industrial partner, and they will get a holistic understanding of bioeconomy in addition to solving a specific challenge. They will be able to connect scientific and technical knowledge, and they will get a bespoke training. And by doing this, we're hoping to kind of nurture a new generation of skilled workforce. And by this, I would like to finish saying thank you firstly to Dr. Guzik for his kind invitation. Thank you to the organizers. And if you want to connect with us, you can use our website, Twitter handle, my personal Twitter handle, or write to us. Thank you.
Thank you very much, Tanya, for this great presentation and great outlook of this, what you are doing there in Ireland with other scientists and industries. With this, I think we came to the end of the presentations for today. I would like to ask Professor Steinbichler to say a few words, commenting and wrapping up all the conference we've been today together.
Yeah, thank you very much for giving me the word. I think we have heard in this morning various very interesting lectures, and my conclusion is that we have to be in the future really specific. There were some specific proposals, some specific suggestions, and we have to do this because no group or no consortium can do all. The life regarding chemical products, biological products, and the remains, the waste, and so are so complex, but there's a good chance to identify some of them and to recycle them by chemical and by biological means, and to reuse them again. But this cannot be done for all substances. We have to identify the most important compounds which represent the most, let's say, voluminous compounds, and then to grab them and to convert them into some useful products. I mentioned the rubber, which has a let's say a high volume among the produced chemicals or isolated compounds, and there are several others. And for these compounds, I think we have a chance to convert them and to include them in a circular economy. And this must be done. We cannot use all these compounds. There will be some remains which can be just like sewage converted into biogas. And I think it's not worth to aim at the reutilization of any compound that is produced by mankind. This will mean that we are approaching the 100% goal like an asymptotic line, and this will simply not be possible. And I think it's also not worth to spend money, the engagement of people for these compounds. They should be just like sewage, just converted into biogas and similar compounds, maybe low carbon length fatty acids. But this portion should be reduced to the minimum. The second conclusion is, and that becomes also very clear from the presentation, but I think it should have been clear before for everyone, this field is very interdisciplinary. There are various disciplines of chemistry, various disciplines of biology to be involved. Only one discipline alone cannot solve this problem. The problems have to be addressed by consortia of scientists majorly from these two disciplines, and of course we also need economics, we need patent attorneys to make this economically live and practically. One other thing which should be clear, I think it's not clear to all of us, but it was very much addressed by the last speaker. We should use the biological diversity, and it was a big surprise. I think it happened about 30 years ago when we learned that only a very minor fraction of the microorganism is known and can be cultivated in the bacteria in the laboratory. That's only about 1%. 99% of the microorganism which exists in the environment can simply not be cultivated in the laboratory and are also in most cases not known. And I think there's a big chance for the identification of new pathways, new catalysts, that means new enzymes, which can be utilized for all these purposes. And that's like in the chemical discipline, also the chemists are looking for new catalysts, and they are successful in finding them. The biologists can also identify new catalysts, and I'm always very surprised if that's not my discipline, but more the discipline of zoology and botany. If I read in popular newspapers that in the jungle rainforest of Brazil, a new pig has been detected. No? And also this has, of course, some biological potential, and it indicates that we are far away from knowing and thereby also exploring the nature in total, and this must be done in the future. And finally, I think there will be no way around if we establish circular economies. That means also to recycle compounds, to reuse the carbon which is in these compounds several times. And only by this, on a long term, we will have a chance to reduce the carbon dioxide which is produced and released significantly and for a long term. And this will be very necessary for the future. And we learned in particular this year, Germany has no earthquakes and other natural catastrophes are really minor, but this year we have learned that strong rainfalls can really extinguish some small villages and hurt many people. And these very strong rainfalls, this is something which happens more often and causes damages also to regions which were so far mostly exempted from natural catastrophes. And if we want to have a chance to survive as mankind, as people, we have to look for these new technical and scientific approaches, and we need the support of the politicians to make the frame for this. The economy and the people alone will not do it. They will look for the cheapest solution because they often cannot afford much more. But we have to force them, and this is the task of the politicians, to go into the right direction. And with this, I would like to close my remarks, and maybe if there are questions, I don't know whether the organizers have left some time to have a discussion now or whether we should close.
Yes, we can. We still have time,
Yeah.
if we have a subject to discuss.
If there are any questions from participants, we can open the floor for the discussion. So please let us know through the Zoom platform. But if it's not the case, I think we can close down this section and have a break. Yes, Kazimierz?
Yes, yes.
Time for a coffee, sustainable coffee.
Sustainable coffee.
What does it mean?
Fair trade, first of all.
During this last comments, I have quickly found something I had in my mind. The website which talks about, I think this kind of organization or concept, but I can read, and I think you maybe we're going into this direction, biomimicry. Biomimicry is a practice that learns from and mimics the strategies found in the nature to solve human design challenges and find hope along the way. Because mimicking the nature is actually the natural way to get back to the reality.
Yes.
Because we went out of actually the reality and we created our own world, which is actually against us.
And I think there are already a lot of examples in the past. No? Lotus effect, for example. That was not something which was discovered by men. They looked how it works in the nature and generated some very useful and powerful applications for this principle. Yeah. And there are many other examples, so we can learn from the nature.
But I think that actually Kazimierz thought about it at a meta level, that we should actually, in our civilization, go back to the environment as such, which has the ecosystem, which all the loops are closed down. So all the materials actually are circling in the environment. And even what you said, that sometimes it's not really sensible to recycle the component, you can go for CO2, but as long as you're actually not feeding the cycle carbon with the new source of CO2 from fossil fuels, it's okay. As long as you have the technology to take out this CO2 back to, well, let's say in this case, plant matrix, right?
You're saying that in nature, most of the compounds are recycled and are not accumulated, but really true, this is also not. Otherwise, we would not have our fossil resources.
Yeah, that's true. Because I mean, because there were times there were no enzymes which can treat cellulose, right? So that's why you have the accumulation of fossil fuels.
And there were also some special physical conditions which prevented the degradation of these compounds and which resulted in a tremendous, huge accumulation of these compounds. And there are also some inorganic deposits from which we profit now for the agriculture, for example, and for other purposes, which also accumulated in the nature. So the nature also has some faults in this regard.
Yeah, that's true.
Last question. Are we talking about two separate, they are not separate, I know, but are we talking about two kind of streams? One is bioeconomy and second is environmental protection or whatever?
No, I think we can combine these because...
Yes, I know we can combine. Should we divide and focus on one and another?
I think they will go in parallel, you know, because gentlemen, here we're talking about two different cycles, the time scales of the cycles, yes? However, we can combine those and revert this what was released from the longer cycle and capture using the technologies from the smaller cycles, so using the enzymes potential to capture CO2 or microbes potential to capture CO2 in that sense. So it for me, I don't know if you agree with me, the both technologies, the environmental protection by circular economy, they are parallel and combined and not separable.
Yeah, I think they must be considered in parallel and cannot be treated isolated.
We had example in the last presentation when foresting of iron is actually the way to consume CO2, right? So it's a bioeconomy, but of course it is focused that way that it saves the environment by first of all producing more plant life to consume CO2, also changing the climate to provide more moisture in the air and so on. So there are different levels for this, right? But actually the focus is economy, foresting industry. So, you know, this is actually a multifaceted problem. connected.
So I have the last citation from that website, which I like. That biomimicry is about valuing nature for what we can learn, not what we can extract.
Oh yeah.
That's true. Okay, thank you very much for joining us here, you by the screens as well. Have a nice day, and please join us in the following section, which will be on
12 o'clock. We welcome you, we invite you to the business development section. That will be the fun.
That'll be fun. Okay, thank you very much, and see you.
Stay tuned.
Stay tuned. Yes.